Good morning to all. Today, myself, Ritik Maiti, will be presenting a presentation on agrivoltaics, simultaneous harvesting foods and solar energy in a temperate climate. So, we will start with the presentation outline, which involves the introduction, the research objective, the literature review, the methodology, research on the basis of energy crop and PAR, and conclusion. We'll talk about the introduction. So, this research is based on the temperate climate zone. So I have taken the site Hungary as a site. Hungary as a site because they are trying to go for the net zero carbon emission by 2030, and also Hungary lies in the Köppen classifications as a temperate climate zone. So as we can see the country's history, the total energy supply chain back in 2023, it was based on with wind solar with covering around 11.1%, natural gas with 17.9%, and other fossil fuels as more than 50%. Back since EU is going forward the net zero carbon goals in 2050, so Hungary is also looking to in a utilize their solar PV potential. So they around 2023 they have also developed solar PV of 88.7% as well as the geothermal energy as 0.2% and wind 8.3%. So we can see from the graph that the annual generation per unit of the installed PV capacity is increasing by percentage, is increasing by year. Okay, and so what is agrivoltaic system? Agrivoltaic system involves the utilization of land for the generation of solar energy as well as for utilization of crop product yield. So it is a win-win situation where both the land is being used for energy generation and for crop yield production. So for this site, we have used Hungary Voplet location as the site because it's one of the site which can be used, which is a site for temperate climate zone. And also this the tool which are being be used be support is validated against the temperate climates. So what are the research objectives? For this, we are using the Hyperfarm AgriPV tool, which is being utilized for one of the projects for agrivoltaics, and it has been validated by the European Union. This Hyperfarm AgriPV tool is to use to determine the annual energy generation in a year at Verplet, Hungary, and to determine the PAR amount, the photosynthetically active radiation amount in areas covered by canopy in a hectare, if there is a potential agri-PV projects, and also to quantify the crop yield increase if the land is used for agri-PV projects. We go for the literature review. Literature review focuses on the effects of the EV system configuration of crop yield and electricity generation by Mamun et al. The key findings existing set of influences in both yield and energy output. Wilcox et al., which focuses on the influence of light condition on crop growth. It's an experimental validation on how homogeneous light is performing well for the uniform crop growth. Morin et al., which focuses on the variation of ground solar radiation in AV condition. It includes the field observation, and the key findings include the ground radiation is key for AV performance variable and critical for shaving and PAR modeling. And Zainal et al., who addresses the microclimatics modeling in AV systems Sweden, which includes the CFD simulation, the key findings on studied irradiance, wind, soil, and the microclimatic factors. And William et al., who studies about the impact of AV configuration on PV model thermal regulation. It includes the method on CFD with evapotranspiration and albedo modeling. The key findings include the cooling effects on the improve of PV performance. Methodology, we use the AgriPV tool. The AgriPV tool is clearly based on the hourly solar irradiation. The hourly solar irradiation we extract from PVGIS, which breaks down into DNI, the DHI, and the zenith angle and the albedo. Albedo is the portion of the light which is reflected from the canopy. The module length we take as assumptions as module length, module width, bifacial factor, and DC to AC power ratio. For this kind of simulation, we have taken assumption as module PV equal to 214 kilowatt peak, and the bifacially and albedo as zero point 0.3, and the bifaciality ranges from 30 to 70%. So when we calculate the incident radiation. The incident radiation is calculated based on the radiation calculation. We compute the DC power and the AC power. The AC power is based on the efficiency of the PV module into the coverage, the ground coverage ratio into the solar PV module install, and the AC power is based on the efficiencies of water. But for this kind of simulation, we are mostly dependent on the DC power. For the crop, we are taking the height, the ground coverage ratio, the transparency, tilt, array width, and the root to root distance. So it calculates by the ray tracing algorithm, it calculates the remaining PAR, the relative crop yield, and the PAR deviation. So as per as what we do in the simulation, we get the electrical and crop yield. As we see from electric yield is more in the July month, and it extremely reduces on October, November, December, because the solar radiation for Hungary for a temperate region is mostly during the June, July, August. So you can see, so we can see that electricity yield of kilowatt per kilowatt peak is highest during July, August, and June. If we go for the relative crop yield, the crop yield also over the year with increase in solar irradiation, it increases. But since it increases, but after some time it reduces due to the decrease in solar irradiation. So the relative crop yield also increases at some point about amount of time, but it relatively decreases after some time due to reduction in light. Okay, so if you can see that 100%, it reaches to the 100% maximum, where the crop yield increases to 40, but again it reduces to 80%, so crop yield decreases. So crop yield is in the form of the percentage form. So for the results PAR, PAR means the photosynthetically active radiation. The photosynthetically active radiation, we can say that in the red ones shows the photosynthetically active radiation are very dense because of the more of solar irradiation, and because of the canopies getting the solar irradiation directly. But the blue one is being shaded by the solar PV. Okay, the solar irradiation doesn't reaches here, but reaches more towards the brown area, towards the reddish area, which shows the PAR. So crop mostly the crops are grown in between this area where the bluish areas are there, because the solar PV panel, and the crop grows beneath the solar PV panel. So for the parameters, what we see, the install capacity, what we observed that 835 kilowatt peak. This is based on the capacity we have taken. Okay, so the capacity we have taken, the energy yield per hectare is 101 per hectare. Specific energy yield 1211.57 kilowatt hour per unit. The remaining PAR as per the, so we see that 52%, deviation PAR as plus minus 20%. So we see that